weld stress analysis. This will be a 30-minute webinar. Your phones have been muted. If you have any questions, they'll be addressed at the end. You can enter your questions in the Q&A or chat windows. So we'll go ahead and get started. The outline of what I'm going to present this afternoon is first the importance of weld stress prediction. Why are we concerned about it? A little terminology just to make sure we're all on the same playing field in terms of the definitions. Primary fatigue failure for welds is fatigue. So we'll spend some time talking about different procedures for evaluating the fatigue failure in welds. And in order to evaluate fatigue failures, we need to know something about the stress state in the welds, and there's 4 different approaches that we can use to determine the stress state in the weld, and we'll go over those in detail, from the nominal stress method, where we're just looking at like a P over A, C over I kind of prediction of a nominal stress, and take into account the stress concentrations in the critical local cracks and everything with an empirical deduction in the weld strength profile, down to the most extensive type method where we actually physically model the cracks in the weld using fracture mechanics, where we can use a stress intensity type evaluation. We'll cover the nominal stress, the Hotspot method, and the notch method in detail. The stress intensity method will be covered in detail in an upcoming webinar where we're going to go through the operations of running fracture mechanics within ANSYS in detail. Mike Bach will be presenting that in the coming months. So, key features of welds. Welds have a sharp change in geometry or sharp change in section. There are local discontinuities. It's really hard to define exactly the weld profile. Because of the way welds are created, we generate heat, we have residual stresses generated, and the cooling process, these become tensile stresses. The material properties can vary over the weld section. The geometry is just not that well defined. And all of these entities lead to a reduction in life of the weld connection joint. And to quantify that, if we look at the condition of a SN curves in terms of fatigue representation, and we take just a flat bar, in this particular example, the endurance limit, or the limit where we have infinite number of cycles, is a stress level of about 300 megapascals. If we take the same bar and put a small hole in it, we see that we get a reduction in fatigue strength down to the area of 200 megapascals. And finally, if we take that bar and we weld a couple plates to it, you notice that we go all the way from 200 megapascals down to about 30 megapascals. So we have an order of magnitude change in terms of the stress level that we can withstand when we start having welded connections. Different weld profiles, different weld geometries will behave differently. Some of the different potential basic shapes in terms of how welds are used to tie plates together. They could be anything from a butt weld, corner joint, T-joint, lap joint, edge joint. And then for each of these profiles, or for many of these profiles, there's also a question of what type of weld. Is it a fillet weld where we're just tying the outside material together, or are we using some kind of penetration weld where actually the weld material is penetrating into the plates? The most durable weld would be a full penetration weld, maybe something like the double-sided penetration butt weld here, where not only do we have a full penetration of weld material, so we have no initial cracks that we would see with a partial penetration, but then also, furthermore, often people will grind out the toes of the weld to eliminate any local crack initiation points to further enhance the fatigue life of the welded connection. And when we use our calculations to go ahead and try to compute a life of our structure, we can take any of these imperfections into account in terms of which life curves that we select to use. Terminology in terms of the weld profile that we're looking at, we have a weld profile that includes the face of the weld, the toes of the weld where crack initiation typically will occur, the weld throat or the thickness when we're looking at nominal stress, how much the stress level, or we're in the design process, what forces and moments can that weld carry, are generally defined based on the thickness of the weld or the weld throat. The root of the weld is down another point where crack initiation potentially can occur, particularly with fillet type welds. So as I mentioned at the beginning, the primary failure mechanism in welds is fatigue. And fatigue is from cyclic loading. And the underlying mechanism of this propagation of cyclic response or propagation of failure is through the propagation of cracks. With all welds, you've inherently created cracks in your model just in the process of performing the welding operation, and those cracks can be of various different sizes. We can use tools to analyze the strength of these welds and the life of these welds using some of the capabilities in ANSYS and also in the sister software ENCODE, where we can take the distress data and plug that in and use the ENCODE to predict a life based on the stress state that we empirically define. In terms of evaluations from the calculations, we can calculate nominal stresses or peak stresses at the toes of the weld using the classic stress calculations, or we can embed cracks and calculate stress intensity factors and use a fracture mechanics type of evaluation. Cracks are going to be persistent in all welds. The size of those cracks is a function of a number of things. One of the things that can cause significant cracks in existing welds is certain types of defects. So different types of defects that will enhance the stress concentration or the crack size in a weld could be anything from not enough penetration, trapped gases, solidification cracking. All these kind of different things can lead to the process of potential embedment of cracks, which can initiate fatigue failure. So from a fatigue failure, if we're trying to predict life, the first thing we do is we need to calculate stresses, and we need to have some means of taking these stresses and then comparing those with material data to try to predict the life of our welds. And there are four methods to which we can use, or with four methods we'll describe: the nominal stress method, the hotspot method, the effective notch method, and the stress intensity factor method. And before I get into detail of describing each of these, what I'd like to do is go ahead and offer up our first poll. So our first poll is, how do you currently model welded connections, if you do at all? And I'll go ahead and leave that up there. So do you model welds at all? Do you use shell elements, solid elements? Do you model a weld profile? Do you not model a weld profile? And again, your answer may change as you go on in terms of what you gain from this webinar or from literature, searches, etc. So we'll wait a couple seconds for everybody to go ahead and answer the question, and then, of course, we'll give live feedback to everybody in terms of, you can see what your colleagues reported in terms of how they model welds. So I see the poll has ended, and wait a second, and Chris will publish our results in a second. Okay, so we have the results. So a good portion of you don't actually model welds, and some of you do, and some of you model them explicitly with the local fields. Okay, well, if you've never modeled welds before, we're going to give you 4 different options in terms of procedures that you could use to model welds in the future. The first method is the nominal stress method, where we're actually not actually modeling the weld profile in any detail. We're basically modeling the plates or what is being connected and pulling stresses or forces and moments from these, using these as a design standard and plugging these into life prediction curves that account for the fact that the stress concentration, the residual stresses from the welding process, any initial cracks already exist in our model. So, nominal stress method as an example, what I can show is, for instance, let's say I, as a problem, had a situation where I had this pipe and it's welded directly to a flat plate, and we have a quarter section we defined in this analytical model, and I'm interested in calculating the nominal stresses at this intersection. Now, I could go ahead and take and use ANSYS to calculate the vertical stress in the y direction, just pull it off in the standard procedure of taking the average stress through that profile. And the average stress would give me a peak stress at that intersection, but it's a sharp corner, and it's actually averaging stresses from the vertical plate and the horizontal plate. So not necessarily a very realistic data point to use. The other option is I could take a user-defined result for just this vertical plate, and again, I can predict the stress there, and that stress may be somewhat relevant, but now maybe I'm picking up a little bit of a stress concentration. So again, not necessarily the most accurate result that I want to plug into the nominal stress calculation. So since the nominal stress calculation is based on forces and moments, the easiest thing to do is go ahead and extract forces and moments from my finite element model. And I can do that by inserting construction geometry. This is in 14.5 a workbench. I can create a surface plane that I make just above the intersection of my 2 plates, so slightly above there. And then in the analysis settings, I make sure that I set the output controls to write out the nodal forces. And then I can insert a reaction probe, and the reactions probe that I can define can be pulled from that surface. I can extract the forces that are defined at that surface based on my local coordinate system that I've defined that's slightly offset from that geometry. And similarly, I can take the net moments through that section as well. And now these forces of moments I can plug into my empirical weld design tool, or if I need to, I can calculate nominal stresses from these to plug into my fatigue calculation. So that's the nominal stress method. The second method we're going to talk about is the hotspot stress method. In the hotspot stress method, we're taking into account the stress concentration effects, but we're not actually looking at the local notch effect at the weld toe. So generally speaking, we're taking the stress in the weld profile and maybe extrapolating that out to the intersection of the toe of the weld, but not actually taking into account the local stress concentration at that point. And if we take this stress and we want to compute a fatigue life based on this stress, then we have to use the appropriate stress strain, or the SN curves, where we have an SN curve that is based on a hotspot stress range at the weld toe. And there's no single way of modeling this analytically, but I'll go ahead and bring up another alternative modeling procedure. Same problem I just talked about before, only now I've modeled it with shell elements. And now what I've done is modeled the weld profile with a diagonal shell at the weld intersection. And I had to define some kind of thickness for that shell. And what you can do in ANSYS is I can go ahead and say, in the view process, go ahead and show the actual profile. You can notice that I made the thickness more or less line up sort of with what the weld profile would look like. And now for my stress calculations, now I can actually go in and look at and pull off a nominal stress in the particular vertical plate, and now I'm predicting a stress significantly higher because I've got this profile defined in there. And take this stress, and what I would suggest is everybody comes up with their own methodology, not necessarily for calculating the stress, but I might take this stress and plug it into some existing known simple problems where I have a known predicted failure at the number of cycles, and see if I can calibrate my analytical modeling technique with test data. One of the things that's sometimes done to calibrate that and to get a consistent result is maybe making the mesh size such that the end element is about the thickness of the weld. So I've seen people do that and pull centroidal data as well. So there's a variety of different ways to extract that data. The next approach we're going to look at is looking at the notch method. Before we do that, you got to be a little careful when you model the weld profile. If I were to model the weld profile as a sharp corner and I continue to refine the mesh, I've now created a stress singularity. I have a reentrant corner. And if I refine the mesh enough, that stress will continue to increase. So I have an arbitrary solution. I have an infinite stress that gets created there. So we have to have some methodology to be able to accurately predict a local stress concentration, but without introducing singularity. And the way we do that analytically is we use what's called the effective notch method. Because once I put a small radii at the toe of the weld, now, as I refine the mesh, I will converge on a stress value. Now I have a known stress value that I can plug into my SN curves and predict the fatigue life of my structure. So the effective notch method, where we explicitly model the local weld profile and we put a local fillet radius at the toe of the weld. And numerically, what has been done to calibrate with test data from a number of different applications is to use an effective root radius of 1 millimeter. The one exception is if you have a very small, thin structure, then you may use a fictitious notch radius of 0.05 millimeters. If you look at test data, you notice that you'll see some curves, such as the one shown to the right, where we have effective notch stress range, and they have an item on the curve labeled out as FAT 225. What FAT 225 refers to is a 5% failure probability at 2 million cycles at a stress level of 225 megapascal notch stress. So analytically, how do I come up with my notch stress? Well, with a notch stress, now our finite element model is much more refined. So we need a much finer mesh in the local region of our weld. And typically, it's not advantageous to create that kind of mesh density in a large 3D model of a welded connection. So different approaches can be done. In this particular example, I took my same problem that I solved previously, Only in this case, I solved it as an axisymmetric solution. So with an axisymmetric solution, I can easily create the 1 millimeter radius and create a fine enough mesh where I can predict the stress in detail locally at the toe of the weld. You see, I get nice uniform contours where the peak stress value actually carries over a couple different elements. That's always a good thing in terms of predicting that. And I can also take the stresses on the edge of that surface and probe to the edge to get the peak vertical stress at that particular location. So if I go back to slide presentation, just the other technique that's often used if it's a 3D profile is submodeling. So in submodeling, I could use a shell mesh for the overall connection, and then to get the weld profile, to get the detailed 1 millimeter notch, I could do that with a local submodel. And it would be advantageous to go through and run a mesh sensitivity study to make sure your mesh density is fine enough to predict that local profile. So this is the third method of predicting the local stress concentration by inherently initiating or defining a small radii. The final approach is the stress intensity method, where we're actually going to run a fracture mechanics simulation. So we actually will embed a crack in our model. And the crack size may be, for instance, the maximum size of crack that can be evaluated by the intrinsic testing or the intrinsic checking of welds. So we know that if we can't see the weld crack, but we can only see cracks to a certain level, we know we can hypothesize that there's a crack at least of the inspection size always existing in our structure. And then we can say, okay, what is the probability of this crack propagating? And embedding the crack into our model is something, again, that I mentioned at the beginning of the webinar, is something that will be covered in a future webinar that Mike Bach will go through the process. And ANSYS has added some new features in version 14.5 to automate the process of embedding a crack into your geometry, and one of the places you can embed that crack would be into the details of the toe of your weld if you modeled the weld profile in detail. So, in summary, we had a series of different methods for calculating the nominal stresses, or the stresses in the weld, from the nominal stress method to the hotspot stress method to the effective notch method to the singular stress method. And just out of curiosity, it's a good time for our next poll question, is what we're going to ask everybody is, which method of stress calculation do you plan to use in the future in your weld designs? Go ahead and leave the profile up for a little bit and let everybody select an answer. And again, we will allow everybody, once the poll is closed, to take a look at what your colleagues have mentioned. And all of these methods have their place. Sometimes the method you select will be driven more by what test data or what data do you know about your weld. If you don't have notch stress SN curves, there's no point in modeling the notch into your model. So you got to look at what empirical data you have that you're going to use from the design, and from that, then you can go back in and develop the analytical model to predict the appropriate stress state that's consistent with your fatigue data. So the poll is ended, so we'll wait for Chris to put out the results of the poll. And looks like we have a fairly uniform across the board. So there are, I guess, the effective notch method and the nominal stress method are the two leaders, since the no answer doesn't really count. So if I look at the different methodologies incorporated into the example today, we notice that we first used the force moment profile, and from that we could compute some nominal stress. We then looked at using shell elements by defining a profile and estimating the hotspot stress. And finally, we used the effective notch method to predict a more accurate stress state in our solution. And you notice that each of these methods produced a higher stress value. And that's consistent with what we saw in the diagram schematic previously. Well, just as a final note, to get some correlation back between these different methods we used and how does that compare to empirical test data, I pulled a couple different data SN curves. One of them is for a X-type connection where we have fillet welds, and you notice that the stress level for the condition of 5% failure at 2 million cycles is a stress of 36 megapascals, whereas the effective notch stress is 225 megapascals. So it's pretty clear that you have to make sure that you're using the correct data that's consistent with the appropriate procedure. And the effective stress data takes a lot of the unknowns out of the equation. However, both methods will take into account the assumption of that there are built-in residual stresses from the whole welding process, that there are some embedded cracks in the model. Those are included in both effects. The addition of the stress concentration effect that we're calculating explicitly with the effective notch, whereas with the nominal method, we're just assuming a particular stress concentration.